Welcome back. In section 2.2.3, we'll be talking about isomorphism of vector spaces. That's what we've been working on since we started introducing kernel and images and one-to-one maps and onto functions. All right, so definition 2.2.5, the inverse of a function. A function g from y to x is the inverse of a function f from x to y. If I apply f then g, then I get x for all x and x. And if I apply g first, then f, I'm going to get y for all y and y. And then if that's the case, then we're going to denote g by f to the -1, f inverse. And a function f is called invertible if it has an inverse. All right, so let's do an example. This is really to play with the notion of inverse. The math isn't too hard. Example 2.2.8, show that the cube root is the inverse of x cubed. Right, so I want to check that if I compose them this way, that means applying f first and then g. So I apply f, then I apply g to the result. Well, that is just x. That's perfect. So really, the cube and the cube root cancel each other, and so I get x back. Same thing if I apply, you could write it to y or to x. Here, the two sets are the same, so it feels a bit artificial to have a different letter. So I'm going to apply g first. That's going to be cube root of y, and then I'm going to cube it. And I'm going to get y out of it. Perfect. All right, I want to look at the square root because it's not the square root, the square. It's quite an interesting example. Example 2.2.9, show that the function f of x equals x squared is not invertible. All right, so this is going to be a proof by contradiction. So I'm going to assume that f is invertible with inverse g. That means g composed with f of any x is equal to x. Right, so let's check what happens if x is equal to -2. Right, so this is g of 4, but also, actually let me show you why. This is g of f of -2. F is just squaring, so this is g of 4. But also, from this right here, I'm going to get that that's -2 because that's g of, sorry, yeah, that's -2 because I get x back, the g and the f cancel. I'm going to do the same thing to +2. So I'm going to get g of f of 2. That's going to be g of 4. All right, so from the first one, I get that g of 4 is -2. But if I keep going with this, from star, I get that g of f of 2 is actually 2. So g of 4 must be 2, and I get a problem. If I have an inverse for f, it must send 4 to -2 and send 4 to 2. That's a contradiction. And so no such g exists. So f isn't invertible. So as soon as you have two elements that are sent to the same one, you're going to run into trouble. And so that's what we put in a takeaway here. If a function is invertible, then f is 1-to-1, or if it isn't 1-to-1, it's not invertible. Here you might ask, what about the cube root, the square root? Well, the square root is the inverse only of this half. It only cancels when x is positive. If x is negative, it doesn't cancel with the square. All right, so in the following proposition, we give necessary and sufficient condition for a function to be invertible. We already have one here. Let's put both together. So a function f from x to y is invertible if and only if f is both 1 to 1 and onto. Right, so we've sort of hinted at part of this before, but that's why we introduce one-to-one. That's why we introduce onto. That's why we gave you criterions for proving something is one-to-one when it's a linear transformation and proving something is onto, because we're after invertible linear transformation. Those are going to be our equivalences of vector spaces. All right, so let's prove this. Assume that Hef has an inverse G. I want to prove F is 1 to 1 and F is onto. Let me say this proposition has nothing to do with linear transformation. This is something about functions and sets. Don't need a vector space to state this. We'll have criterions that are specific to vector space involving the kernel, but for now, okay. All right. I want to prove that F is 1 to 1. So take F of x1. This is 1. This is 2. F of x1 equals F of x2. Then I can apply G to both sides. Sorry. G of F of x2. And then G and F cancel. So this is x1 and this is x2. So x1 is equal to x2. All right, so we just proven that F is 1 to 1. Now I want to show that F is onto. All right, so I'm going to take y and y. I want to find an x that's sent to it. So I'm going to take x equals g of y. All right, if I apply f to it, I get f of g of y, f and g cancel, and I get y. That's exactly what I wanted. And so f is onto. All right, so we've just proven that if f has an inverse, then it is 1 to 1 and it is onto. Now we're going to prove the opposite direction. I'm going to assume that f is 1 to 1 and onto, and I'm going to build an inverse. So take y and y. Since f is onto, there is an x in x, so that f of x is y. And so we're going to define g of y to be x. Right, so if I look at, so I want to prove g is the inverse of f. So let's prove one direction. One direction is actually easier than the other. All right, so by definition, this is f of x, and we've picked x so that it gives you y. All right, let's do the other side. If I have g composed with f, and let me call it x1. because I don't know it's this x yet. So I'm going to apply f to x1. This is going to give me some y. And so I'm going to get g of y, which is going to give me x above. How do I know that x is x1? Well, we've picked x, so that f of x is y. But f of x1 is y as well. And so here we need f to be 1 to 1. X equals x1, and so this is x1. Oops, sorry. And that's what we wanted. All right, let me shrink this a tiny bit. And so we have that g is the inverse of f, and so f is invertible. All right, so if a function is both 1 to 1 and onto, we're going to like it because it's invertible. So let's give it a name. So if a function is 1 to 1 and onto, we're going to call it a bijection. So a function is called a bijection if it is both 1 to 1 and onto. All right, so in what follows, we'll look at bijections that are also linear maps, and those are going to be our equivalences of vector space. Those are what we're going to call isomorphism.